All right. Hello to everybody. And I have a technical difficulty here. Let's see here. All right, sorry about that. We'll start over here. I had one of those things where my computer wanted to reboot. So hello to everybody. Thanks so much for joining us. I'm Kevin Murphy with the Office of Water Programs here at Sac State, and we're happy you are attending our first of two Spring 2025 Water Seminar Series presentations. As most of you know, we are a training and research organization with a focus on water quality and water resources, and we annually host two fall presentations and two spring presentations. So following suit, we'll have one more presentation this spring, which will be on April 18th, when Arthur Umbel presents on circular economy. I also want to point out that all the presentations we host are recorded and can be accessed via the Office Water Programs website. So today's presentation will be about 40 minutes long, so we should have about 20 minutes left for questions at the end. We can go a little beyond 1 p.m. to answer questions if necessary. If we simply don't have time to cover all the questions, I'll forward the questions to today's speaker, Ren Brownell, as she has graciously agreed to address them via email if necessary. Please submit questions by emailing them to the email address currently showing on the screen, which is seminarquestions@owp.csus.edu. You can take a screenshot or also check the chat line where the email address is also provided. All right, so now for the important part, I want to welcome Ren Brownell. Ren is going to tell us about the removal of multiple dams up north on the Klamath River. Ren is the Public Information Officer for the Klamath River Renewal Corporation, the nonprofit tasked with the removal of the 4 Lower Klamath dams and the restoration of the formerly submerged lands. She holds degrees from UC Santa Cruz, go Banana Slugs, and University of Oregon, go Ducks. And she has experience working with agencies, tribal governments, and communities to create effective communications and consensus to support restoration activities. And with that, I'll hand it off to Ren.
Good morning, everybody. Thanks for such a nice introduction. I just want to make sure first that everybody can kind of see my slideshow. Is that up correctly? Looking
Yes,
good?
we can see it.
Great. So I'll spend the next 40 minutes just giving you an absolute crash course in how we took these 4 dams out in such a short amount of time. And then, like you said, I'm happy to answer any questions you may have. I should give the caveat that I work mostly in communications. I know a lot about dam removal, but I am not a water quality specialist, but I will share some of the positive effects that we're seeing towards the end. So first, these are the 4 dams that were set to be removed. I want to start off by noting that these were all hydroelectric dams. None of these dams were operated for flood control. They didn't store water for irrigation purposes. They were strictly hydropower, and they were really meeting kind of the end of their lifespan. At the time that we removed them, they were generating about half the power that they originally could when they were built. Now these dams essentially bisected the basin. So on this map, you can see the whole Klamath Basin, and you can see where Iron Gate was the lowermost. Copco 1 and 2 were sandwiched really close together, and then J.C. Boyle was farther up. That's the one dam that was in Oregon. So the reason that folks advocated for the removal of these dams was really to preserve the salmon runs that are left in the Klamath River. So currently we're having runs that are about 3% of what historically would come out of the Klamath. And first and foremost, you can see again how they bisected the basin. None of these dams had any sort of fish passage on them, and so they blocked about 420 miles of spawning habitat between the Klamath and its tributaries. The other issues that they had is that there were unnatural impoundments along the river that allowed the reservoirs to kind of sit out in the hot sun that create abnormal temperatures that cause toxic algae blooms, impaired sediment transport, and those issues led to the exacerbation of fish disease in the basin. So those are the reasons these dams came out. So first today, I want to talk to you about COPCO number 2. This is the dam that we took out in 2023. And on my screen here you can see this canyon that usually is not seen. It's called Ward's Canyon. So back in that other, that kind of overview, you could see that COPCO 1 and 2 were sandwiched right next to each other. And you can see that right here. So COPCO number 1 is at the base of that reservoir on the right-hand side. On the left-hand side, you can see the beginnings of the Iron Gate Reservoir. And then you can see COPCO number 2 located shortly there below COPCO number 1. Most people had never even seen a picture of COPCO number 2. In the fight for dam removal, people shared lots of images of COPCO 1, J.C. Boyle, and especially Iron Gate. But this dam was significantly smaller than the other dams. It only stood 33 feet high compared to Iron Gate's 180 feet. And it was located in this very remote canyon. When you talk to folks who live around the COPCO Reservoir, some of them didn't even realize that this canyon was situated right downstream of them. And while this dam was very small in size, it had a significant impact on the landscape because it diverted waters at that point where you can see the little icon, funneled all the water out of the river into a tunnel that went under the mountainsides and then popped out at the powerhouse about 1.7 stream river miles down below. And then that kind of started the top of the Iron Gate Reservoir. So this dam, though very short, essentially dewatered 1.7 river miles. So this is what COPCO number 1 looked like prior to removal. At this point, the water's no longer being funneled through the tunnel. We had already turned off the powerhouse. The water's going down the canyon. I want you to observe that there's trees down below and in the river, right? And that's because in the absence of river flows, trees had grown up in the riverbed. And this is what it looked like after removal. We had a really unique opportunity with the removal of this dam. Because it was sandwiched between 2 reservoirs, we could actually hold the water back in the COPCO Reservoir and maintain downriver flows out of the Iron Gate Reservoir and completely remove this dam in the dry. So there were no turbidity impacts associated with this dam's removal. And so this is what that river canyon looked like before dam removal, those trees in place, and we did remove those trees, and this is what that canyon looks like now. We removed those trees because once they were exposed to consistent river flows, they would have died and fallen in the river, which would have made for good fish habitat, but would have posed a drowning hazard for the boating community, which is very excited to come and raft this section and kayak this section of the Klamath River, right? It's a bit of river that's been inaccessible for 100 years. COPCO number 2 was completed in 1924. And also, there's a ton of drop in this section, right? That's what made it a good place for a hydropower dam. That's why they put 2 in this canyon. There's an incredible amount of drop, so it should be a fun, rowdy time moving forward. So COPCO number 2 was removed prior to the other 3 dams because it didn't have a reservoir behind it. It was simply a diversion dam. The other 3 dams, we had to first implement drawdown, or the slow draining of the reservoirs, right? All the water they were holding back had to be drained before we could begin removing them. And we had a couple of serious considerations that came along with that. The first one is that there's lots of communities that live downriver of these dams. They were about 200 miles upstream from the ocean. So I think the greatest disappointment I often heard from people is that they wanted one big explosion and a rush of water and dam removal would be over. And that is a strategy that they use on other dam removals, but those are dams that are much closer to the ocean and that don't have communities down below them, right? Because that can be a really good strategy for sediment evacuation, which was one of our main concerns. So we knew that we had to drain the reservoirs, again, at a rate that would not impact communities downstream. So we knew we could not go above 3,600 CFS. That would keep us from overtopping the usual winter high water mark on the river. But we also had to time this very carefully because as those dams stood in place, they impounded an incredible amount of sediment. Some of that sediment is what was coming down of tributaries, naturally coming down the river and getting stopped by the dams, right? Sand and gravel transport is a natural part of any river system. But the majority of the sediments behind these dams were actually dead algae. Like I noted earlier, one of the main reasons for the removals is that this water was sitting out in the sun and would create these huge toxic blue-green algae blooms. Now in the fall, the algae would die and would sink to the bottom of the lake. And that process was happening for over 100 years in the case of Copco Reservoir. And so that ultimately impounded about 15 million cubic yards of sediment, and about 90% of it was just dead algae. And we knew that during the drawdown process, right, as the rivers or the reservoirs drain, sediments get stirred up. The river has to carve through these accumulated sediments to find its historic riverbed. And the danger with dead algae, dead organic matter, is that when there's dead organic matter, you can think about trees as well, sitting at the bottom of the lake, they don't have access to oxygen to decompose. But as the reservoir drains, those sediments get stirred up, they have access to oxygen and they will deoxygenate the water around them. So we knew that during this drawdown process, we were going to crash the dissolved oxygen in the river. And that essentially would suffocate fish in the river. And so we knew we had to time this very carefully, and we worked with agencies, federal and state and tribal fish entities that directed us when to implement this drawdown process. And so for that reason, we did it between the months of January and March, with the thinking that the fall run had already come up and spawned out, and the juveniles were not out migrating yet. So those were the serious considerations. So to drain the Iron Gate Dam, we were able to utilize existing infrastructure. You can see this is actually the day we initiated drawdown at Iron Gate over a year ago now. This was January 11th of last year. And so that tunnel there, it's called the Low Level Outlet Tunnel, and it's actually original to the dam's construction. This is a photo when Iron Gate was being built. So the first thing they did when they arrived on site is they blasted a tunnel through the hillside, built this dam back here, a smaller dam called a cofferdam that would divert the flows around their construction site so they could build the dam in the dry. And with just a few modifications, we were able to utilize this tunnel to drain the Iron Gate Reservoir. And this is what Iron Gate looked like after it was drained. Iron Gate, at the tunnel, there was also a gate. So that was good because we could control the rate of flow going downriver. And we could also control how slowly this reservoir drained. You'll see in a moment, and I didn't realize this until drawdown occurred, but the reservoirs were actually very, very different, at least the landscapes that were underneath them. So Iron Gate was actually very steep and very narrow, and you'll see the contrast to the Copco Reservoir in a little bit. So this is a tributary to the Iron Gate Reservoir. This is called Jenny Creek. This is a couple months before drawdown. You can really see the blue-green algae issue that I'm talking about here. And so again, this is probably September of 2023. And this is after drawdown is complete. And this is a good image where you can see what I'm talking about sediment-wise. So out over here on the far left, you see that really dark material. That's that dead organic matter. That's all the dead algae. And then the lighter materials you see are all the sands and gravels that were naturally coming out of Jenny Creek, but they'd hit the flat water of the reservoir and stop there. And so sediment distribution-wise throughout the reservoirs, you would kind of see a very uniform blanket of dead algae across the reservoir, right? In the case of Iron Gate, it was like 2 to 3 feet deep in different places. But then at Jenny Creek, there's up to 20 feet of accumulated sands, and our restoration contractors actually had to do a significant amount of work to kind of help this stream find its natural path again and create good habitat in this area. So I'm jumping upstream now. So that was the draining of the Iron Gate Reservoir. This is the drawdown. This is an image of the blast at the JC Boyle Reservoir. Much smaller reservoir, much smaller dam up in Oregon. It had culverts that were left in place at the base of its spillway, so we just had to blast out some concrete plugs and to drain this reservoir. Like I said, Iron Gate took a little over a month to drain. In contrast, JC Boyle took 17 hours. And you can see from this image that it's a much smaller reservoir than Iron Gate. So Copco number 1 was the biggest one that we had to prepare for. And that's because like I said, at JC Boyle and at Iron Gate, there was existing infrastructure that we could utilize to drain those reservoirs. At this dam, our engineers looked at the existing infrastructure and deemed it to not be safe. So this is another image of Copco number 1 being constructed in this case. And you look kind of down towards the bottom center and just to the right there, you can see a tunnel with water coming out of it. So that was the same diversion tunnel like they had at Iron Gate, but at Copco number 1, this tunnel was constructed in 1911, and our engineers deemed it to not be a safe option, right? You think about how much, there's about 50,000 acre-feet of water held back by this dam, and they were worried that this tunnel just simply could not take that pressure and it would cavitate. And so in the case of this dam, we made our own tunnel. So we blasted a tunnel through the base of the dam. You can kind of see this in this bisection here. So we went 100 feet through the base, left a 10-foot chunk of concrete on the uphill side, and then on the exterior inserted this long steel pipe. And that's because the sheer force of water coming out of this tunnel we knew was going to kind of blast the earth apart. And we were worried about creating a scour hole right at the base of the dam that could potentially cause instability. So you had this pipe that went out to create that scour hole a safe distance away from the dam. And then on top of that pipe, they put a bunch of rock and concrete to make sure that it stayed in place. And this is what that looked like after that was completed. So you can see our outlet pipe there on the right-hand side where that kind of yellow pipe's coming out of the hole in the hillside. That's the original diversion tunnel that we weren't going to utilize for drawdown. And then, Kevin, let me know if this doesn't come through right. This is the drawdown initiation day at Copco number 1. So this was January 27th of last year. So you can see kind of that burst of brown below it. That's not sediment from the reservoir yet. Like you saw on the drawdown initiation image from Iron Gate, at first the water was pretty clear. It took a while for sediments to get stirred up. That is, again, just the pressure of that water blasting the earth apart. If you saw that kind of jet of water that went straight up, that was because there was a manhole in that pipe, because it was one guy's job to go down in that tunnel with a raft, load it with explosives, paddle to the back of the tunnel they had blasted, mount the explosive, get out of there, and then blast this out. So Copco drained a lot faster. Just want to make sure I didn't skip a slide here. Here we go. So Copco drained faster, and that's because we had made this hole a very specific size, and it was based off of a 50th percentile water year, right? All the planning for dam removal was based around a 50th percentile year. Of course, we get to last January, and we are nowhere near close to that, which meant that the reservoir was going to drain at a much faster rate than we were expecting. And when I was going back to drawdown considerations, the one that I didn't note during that time was that we were also concerned about slope stability around the reservoirs, right? Because the reservoirs, when the wind would come through this area, would lap against the hillsides and cause erosion. And our concern was that if we drained the reservoirs too quickly, that the water would come out of these hillsides too fast and potentially cause slope instability. So we needed them to drain at a very specific rate to avoid that. Fortunately, our engineers saw this dry season coming, and we had made a water exchange with the Bureau of Reclamation. So we sent some of our water downstream in an exchange, banked water in Upper Klamath Lake, and that drawdown initiation day that you saw, we sent that water downstream to make sure that the flows were high enough to achieve the drawdown rate that we were looking for. And that strategy worked. The homes all around the reservoirs and all those hillsides stayed in place. But as a result, we still didn't have water to maintain that rate throughout the drawdown process. So this reservoir drained in only a week and a half. And this is a time lapse of that. So, like I said, about a week, pretty crazy to see. So, and this is what the reservoir looked like after it was fully drained. So here you can see what I was saying, compared to Iron Gate, a very different shaped reservoir. And you can also see kind of that uniform coating of algae that I was talking about. The other thing I see that's really exciting in this picture is that you don't see in a lot of rivers in California is the beautiful sinuosity, right? This river really winds all over this ancient valley. And it's because that, you know, when the Army Corps of Engineers came up through Northern California in the 50s and straightened out a lot of rivers that wound through valleys like this for agricultural purposes, this stretch of river was under the reservoir waters, and so it was spared that fate. So as the reservoir waters began to drain, crews got to work immediately with seeding the area. Now, wintertime is not really the ideal time to be putting down seed, right? Really late summer, fall is a better time of year. But again, our priority was protecting the salmon in the river, since at its core, this is a salmon restoration project. But still, crews seeded all 2,200 acres of newly exposed lands because it was important to get vegetation going so that we could stabilize those sediments. So we were impairing water quality for as little time as possible. So crews had been working for about 5 years in advance of this project, collecting native seeds around the reservoirs. So the initial round was 98 different varieties of natives. They collected about 13 million seeds in total. Those were taken to native plant nurseries. They turned that to about 17 to 20 billion seeds that we're using for the restoration process. And the reservoirs are seeded using a mixture of hand seeding and aerial seeding, depending on the area. There's a couple different mixtures. They apply to different landscapes. So this was right after drawdown, and then this was early spring last year. This is the Copco Reservoir. So just to give you an idea of how the restoration went last year. Since then, crews this last fall seeded everything again, including both rounds of seeding. We've applied over 100,000 pounds of native seed to all the different reservoirs. And I expect that it should be looking really, really nice this summer, because I actually would joke with the restoration crews, you can't quite see it in this picture, but the poppies really did well growing in that all that dead algae. And at certain times, the reservoirs were almost looking a little gauche. They were so orange. So the reservoirs are finally drained. Restoration is underway. We can finally start with the deconstruction of the dams. Copco number 1 was first because it's a big concrete dam. J.C. Boyle and Iron Gate were earthen dams, which essentially means they're just a big pile of rocks. And so we couldn't work on them through the spring because the concern was that if you just have these little holes at the base of the dams, right? And if you get a big enough flow of water, right, into the system, a big enough spring flow, you could potentially refill the reservoir and overtop a partially taken apart dam. So we had to wait until the hydraulic conditions were such that we were not going to get a big enough flow for that to happen. But in the case of Copco number 1, this is a big concrete dam, right? You could be halfway through Copco number 1, have a big flow that overtopped it, but it would stay in place because it's a big concrete arch dam. So we started with this one first. The disassembling of Copco is pretty straightforward. It's a process of drill a hole, pack it full of powder, blast, excavate the material, and repeat. So I'll just show you really quick. That was the first blast at Copco number 1. That was the test blast. And after that, they moved forward. It took about 17 blasts in total to take this dam apart. And so, like I noted, it's a blast. You excavate the concrete, chip away at the fractures, remove all the material, and then repeat. This was the largest blast to occur at Copco number 1. They took off 27 feet all at once with this one large blast. And something I didn't know earlier, and I definitely should know now, is that you can see, you might be wondering, where's the river? We actually were able, once we were down to baseline flows, to utilize that diversion tunnel. So the river is actually going through that tunnel around the site and then coming out below the construction site. So just a reminder of that, this is what Copco number 1 looked like previously. And then that's what it looked like when it was done. We had to go underground in the case of this dam as well. It was 125 feet high, but when they went to construct this dam, this area, as you can see, is very volcanic. Lots of columnar basalt, lots of cinders, not a lot of good hard rock to mount your dam to. So they found good deposits of andesite on either side of this canyon. They couldn't find good bedrock to mount the dam to, though. So they kept digging and digging and digging until 125 feet down. So this dam was 125 feet tall and also extended 125 feet below the earth. We did not remove the whole 125 feet underground. We went about 20 feet down and then backfill with area rock and materials. So the deconstruction of J.C. Boyle, you can see that it is half, this is the first day we started taking apart this dam. You can see that it's half earthen dam, half concrete spillway. And then you can see that there's that little barrier up behind it, kind of right below the title there. That's the coffer dam for J.C. Boyle. So in the case of this dam, the historic riverbed was actually under the earthen dam portion. right? So when they built this dam originally, they built the concrete spillway, made a dam to divert the river over to the spillway, then constructed the earthen portion. And we were able to take it apart essentially in the reverse. So at this point, you can see we've removed the earthen portion. There's the historic river path. And then we were able to break through that little cofferdam. That's this right here. And then once the river was moved over, they removed the concrete spillway and capped off the whole area. So this was what J.C. Boyle looked like about a month after that cofferdam breach. It was pretty quick work to take care of everything else. Again, this dam was also much smaller by comparison compared to the other ones. So Copco number 2 was the smallest, was 33 feet high. J.C. Boyle was about 64 feet high. Now, Iron Gate was the most complicated and the largest, right? Iron Gate stood at about 180 feet tall. And it was all a clay core earthen dam. So like I said, just a big pile of rocks. And we had to wait until conditions were right to start taking this one apart, as I noted before. And the way you take this dam apart is that you scoop it up and you move it. All the material to construct this dam was harvested on site. I'm going to jump forward here and show you this. So this is prior to us taking apart the dam. So you can see that we set up some offices right here. But this big excavated here where there's no trees really, there was a slope there that they took apart to construct Iron Gate Dam. And what we did is basically pick up all that material and put it back where it came from. So I'll jump back to this image real quick because that's what you see going on here. Those excavators, they look teeny tiny from this perspective, but they're huge. Those are about 40-yard dump trucks. And the dam in total was about 1 million cubic yards because it was 180 feet tall and then it was about 1,000 feet wide at the base. Now that little tower that you see standing there remained because that is what's holding up the gate to allow the flows to go through the low level outlet tunnel. So this is what Iron Gate was looking like when we had very nearly removed the whole dam. You can see that tower still standing there because water can only go through that low level outlet tunnel while it's holding up the gate. You can see that original cofferdam we saw in that historic photo. You can see that they're prepping the riverbed below. Now, this was another very stressful time of the project. I noted that like drawdown, we knew that these DO impacts were going to happen. We knew we were going to have a huge sediment transport. But with each of these cofferdam breaches, there was also going to be sediment impacts, right? Because we're breaking through these little dams and restoring the flows. Up at J.C. Boyle, you saw in that image, if the water was murky for a bad day, we didn't see huge impacts. But then again, that was a very small dam, right? At Copco, we actually didn't see sediment impacts from the breaking of the cofferdam because we had made that tunnel, right? And we made the tunnel right at river height. So there was no accumulation of remaining sediments on the backside of the cofferdam. At Iron Gate, this was a bigger challenge because the low-level outlet tunnel was built at a slight angle like this, right? So the river wants to be here. I hope you guys can see my arms, but the tunnel's at a slight angle. So that's why in these images, you can see that throughout the dam removal process at Iron Gate, there was kind of a pool of water behind Iron Gate. And that's because the water did have to backfill a little bit in order to reach the low-level outlet tunnel. Apologies, I'm experiencing a fire alarm on my house that I'm sure will stop momentarily. There we go. So we knew that there was still accumulated sediments on the backside of this dam. We did some work to remove those. I think a lot of folks were very hopeful that we had stirred a lot of them up and they had already gotten oxygenated through the drawdown process. But unfortunately, not as much as we'd hoped. And so when we did break the cofferdam, this is the cofferdam breach day, those sediments were not oxygenated and they went downstream and we did see another dissolved oxygen crash, which was well within the scope of what we expected, but we were all really hopeful that it might not happen. Fortunately, we didn't see impacts to the incoming salmon. So this cofferdam breach occurred at the end of August. So a very stressful time. Fish were already making their way upstream. The DO impacts, and let me put this into perspective, I should have noted this before, is that when we did do drawdown, we did see DO impacts as we expected. Fortunately, there were way less than we anticipated, right? Some models showed that we could see up to 2 weeks in the Klamath River with 0% dissolved oxygen from stem to stern, right? But instead what we saw is we had 2 days of 0% dissolved oxygen from Iron Gate to Syed Valley, which is about a 60-mile stretch of river, and that occurred twice. And we did see some mortality, right? Because even though the fish aren't in the river, even though the salmon aren't in the river during that time, lots of other critters live in the river. So we did see some, some dead trout, things like that. But we saw the mass die-off of the fish that lived in the reservoirs, right? So you had a lot of non-native species that we, to be frank, didn't want to see populating the Klamath River, right? So a lot of perch, bass, bluegill, and the likes, catfish, all that really like to eat salmon eggs. So we saw the mass die-off of those non-native fish in the reservoirs. So jumping back to August here, when we broke the cofferdam, we did see another dip in dissolved oxygen. It was definitely a hard thing to see. I have to say that after this entire project, I joke with my coworkers that we have DO trauma, right? Because I can look at a river now and I can tell when it's starting to have dissolved oxygen issues. There's some visual signs. But so this was a very exciting day. This was a day of a lot of celebration because with the breaching of this cofferdam, it meant that there was fish passage up the Klamath River. We had already done this up at J.C. Boyle. Of course, Copco 2's gone, Copco 1 is gone, all the other dams are gone. This is the last dam to have its cofferdam broken. So it was a huge day of joy, followed by a rough 12 hours thereafter when we saw the DO crash. Again, fortunately, the fish were farther on downstream. We did not see impacts to incoming salmon, but a hard time nonetheless. And here you can see, right, the water quality, the huge change in water quality. So this picture was taken, that image that I showed you of the day that Copco is fully removed, you could see how good the river looked there, right? Because there were no more sediments to wash out. But because of the nature of this low-level outlet tunnel and the cofferdam, this one still had accumulated sediments, and you can see how dark the river looks there. And actually, this picture isn't it at its worst, because what you can see where the cofferdam is that there's bubbles, right? So this is actually the DO. This is at this point the dissolved oxygen is rebounding, but this is on coming back around, and the river was looking pretty rough. So they broke the cofferdam and they created a pretty narrow channel, and they did that to maintain access to the far side so they could take out that tower that I was describing. And once we saw just how much deoxygenated material there was still behind this cofferdam, we slowed things way down. So we broke this cofferdam, like I said, at the end of August, and we could have had dam removal wrapped up in a week or two thereafter. But knowing how much of this material, again, still was deoxygenated, we took a very slow approach instead. So we peeled back the cofferdam bit by bit to ensure that we did not have DO impacts, again, moving forward. And that strategy, like I said, this was a stressful time, but that strategy was successful. And so this is Iron Gate, the day we initiated drawdown, January 11th. And this was Iron Gate after the dam was fully removed. And like I said, I'm very proud of all the scientists and all of our contractors that we work with. Like I said, once we saw just how deoxygenated that material was, everybody came up with a plan to make sure we had as little impact as possible moving forward. And again, it worked, right? It took a while for the water to clear, for the fish to want to come up, but it was a day. So the day after this picture was taken, Iron Gate completely removed, crews are demobilized, the fish started coming, and they didn't stop. So in the 2 weeks after Iron Gate was fully removed, there was over 6,000 fish that passed by our monitoring equipment at the base of Iron Gate Dam. And I was at Jenny Creek, so that slimy green spot that I showed you kind of earlier on in the presentation. I was standing at Jenny Creek, seeing the first salmon arriving at Jenny Creek with a journalist from Oregon, and she asked me, "This is amazing to see. How long do you think it'll take for them to get to Oregon?" And I was like, it's hard to predict, right? There's a lot of new territory for them to explore. Tough to say how fast they'll find their way to Oregon. And when I got back to cell service, they had already made it to Oregon, right? These fish, I can't imagine how good it felt too to get past that point at Iron Gate and hit the crystal clear water, and they just kept on going. So I know that in Oregon, in Spencer Creek alone, they saw over 1,000 fish. Crews are still working on seeing how many fish, right? It takes a long time to process the data that they were collecting, especially at Iron Gate. We know 6,000 fish passed in the first 2 weeks because there's sonar equipment down there. And so, and they're working on softwares to automatically be able to scan all of that, but presently it's still being hand counted by people. And so we won't have a final number on that for a little bit. And the returning numbers of salmon overall this year in the Klamath River were low. They were in the Sac too. But it was already projected to be a bad year, right? I mean, that's why dam removal was a critical step. The salmon numbers in the Klamath were ailing. The commercial and sport fishing seasons were already closed this year. This was not going to fix the fish run this year, but it inspires a lot of hope for years to come. And while like the dissolved oxygen impacts and sediment impacts that we saw in the short term were really hard to see, it was immediately gratifying to see how many fish took advantage of all of this new habitat. And in the months following dam removal, we saw some of the other benefits come to fruition, right? So in the month of September, the river below Iron Gate was an average of 4 degrees Celsius colder on the daily minimums, and that's 4 degrees Celsius. And in the month of October, it was an 8 degrees Celsius drop in temperature. So you're going to see way better temperature regime in the Klamath River moving forward. And that was a really hot October too. So we're already seeing some of those benefits, which is exciting. And I just wanted to leave you with this. This is what all 4 points in the river look like. Well, this was towards the end of last summer. So a lot of these places are under snow presently, but there's your crash course in dam removal. And I even had 4 minutes to spare, so I have some time to answer some extra questions.
All right. Thank you very much, Ren. That was fascinating. I loved all the photos, and I loved the explosions. Let's see. So we have plenty of time for questions. If you still want to submit questions, please submit them to the email address provided on the chat line. And I will ask the questions to Ren. So Ren, there are a few questions that have come in. Let's see, how did the project get funded, and what were the biggest lessons learned from the project?
So the project is funded through a combination of funds. So I guess I'll jump back in time briefly and say there was a lot of different attempts to make this dam removal project a reality. And the one that was successful was the amended Klamath Hydroelectric Settlement Agreement. So there's about 36 signatories to that agreement in total, and that includes the tribes on the river, states, state and federal agencies, etc. And they're the ones who, through the signing of that agreement, created the nonprofit that I work for, that then created the plans for dam removal. And the KHSA also outlined how it'd be funded. So the main funding comes from PacifiCorp, right? So the original $450 million budget is split by PacifiCorp and then this California Prop 1 water bond. That was a budget that was set in 2011. So, a couple years later, they realized that probably was not going to be sufficient by the time this project came to be a reality. And so they also allocated an additional $50 million of contingency funds. And that is split 3 ways by the states of California, Oregon, and PacifiCorp. So that's the $500 million budget in total. And what was the second part of the question? A lesson learned?
What were the most significant lessons learned from the project?
I have a lot of different takeaways. I think that one of the best lessons that we can take away now is that we can accomplish incredibly hard things, and you don't need speed to be incredibly powerful to do them, right? The reason dam removal came to be a reality ultimately was through an incredible amount of collaboration, right? If anybody tells you that they single-handedly accomplished dam removal, they're telling the story wrong, because it took thousands of people, community members up and down the river, the tribes, people working at the state, people working at NOAA or U.S. Fish and Wildlife, people dedicated to seeing this entire project come to reality. But it all started with community members, right? It started with people on the Klamath River indigenous people who looked around and saw that their river was sick, and that if they didn't do something to fix it quick, who knows what would happen, right? And so it started as with community activists that made this all happen. You had just a small group of people in a really rural part of Northern California who took on the richest man in the world at the time and was able to accomplish this to heal a small part of their community. The other thing that I learned personally through this project is that restoration is hard, right? Like dam removal, the removal process itself was not pretty all the time. And it was incredibly challenging, right? That we got a lot done in a year and a half, but it was not easy. So restoration is challenging and it is messy, but I will also say that it is entirely worthwhile, right? All the pain that I felt during the drawdown process was healed the moment I saw the first fish, and then they just kept coming after that. So I guess like my big takeaway is that the river is resilient, we're resilient, and we are able to accomplish a lot, even when we don't have a lot to work with at first.
All right, thanks, Rin. I'm just going through the questions here. Let's see. This one says, thank you for the great overview of the dam removal project. Currently, what GIS-based tools are being used to help monitor the post-dam removal? Are tribes involved with the use of the GIS-based tools?
Well, I can't speak to what specific GIS tools are being utilized, but I can talk about the incredible amount of monitoring being done, right? So a lot of I suppose I'll start with talking about Resource Environmental Solutions, which is our main restoration contractor. A really pivotal moment in this project being able to be completed was Res taking on a part of this project, because there was at one point when we were, applying to be able to do this through FERC, our main regulator, the Federal Energy Regulatory Commission. They were like, so KRRC takes on all these lands, you take out the dams, you throw some seeds around, but who's to say that that restoration is successful? So they required us to be able to find a contractor that could commit to the restoration being successful. And Res was able to take that on. So they'll be on site for years to come until they've met a couple different metrics for success. Some of those are how much vegetation grows in, each square meter, right? And then a lot of them, though, are actually tied to water quality. So a lot of the monitoring that we do here forward is vegetation monitoring. How many invasives are in the area, how much of it, much of the plant growth are native species. Water quality monitoring, there is a ton. And with both of those projects, they collaborate with the tribes. Actually, I saved it earlier. Let me see if I can still, I'm gonna stop sharing my screen for a moment here. I saved this earlier. There's the Cutting Tribe has a water quality monitoring website where you can go and view live data, right? So you can currently go see how much, what is the water temperature in the river, what's the turbidity, what's the dissolved oxygen, what are the flows, and there's different points all up and down the river, and that monitoring project is directly timed to our permits, and that'll go on for 7 years plus. The vegetation was done in collaboration with the Yurok tribe, and I know that they work with Res to monitor the success of that vegetation. And then they also are working with Southern Oregon University on kind of a long-term study about how successful it is. So there's some of them. I apologize that I can't say that from a GIS perspective how helpful that was, but those are some of the monitoring things. Oh, and the last one is LiDAR surveys, right? So there's a lot of research that goes into what was the sedimentation of the river before dam removal, during dam removal, and then after dam removal into the future. And that monitoring is done through water samples, right? Like to assess how much material was moving through the system. For example, I told you that we expected 3 to 5 million cubic yards of material to travel through the system during drawdown, but it will be USGS who took water quality samples kind of along the way that comes up with the final estimate of how much moved. And then they will actually test the sediments, out of the river bars for years to come to see how kind of the sediment composition has changed, but it's also monitored through LiDAR. So we did a lot of LiDAR prior to dam removal of both the reservoirs and rivers. And then over the next 2 years, they'll do more of that so that they can compare. So there's some example of some of the monitoring, and I apologize that I can't answer the question more precisely about GIS.
All right, thanks, Ren. Next question, were heavy metals from mining part of the sediment bed considerations? If so, how were they handled?
So they were not, because there was not an incredible amount of mining done in this reach of the river. So I apologize, I'm hopping around so I can send everybody this link. Oh, that might have just gone to the organizers. If you could send that link to everybody, that's where you can go and look at water quality. In regards to heavy metals, there were heavy metals present in the sediments in the reservoir, right? Like I said, these creeks were pumping in stuff right outside of the algae. But these heavy metals were not from industrial runoff or anything like that. And while downriver from the dams, right, kind of in the middle Klamath River to lower, there was an incredible amount of mining done, and there is definitely remnants of heavy metals in that regard. Where the reservoirs are, there wasn't mining done there. It's a very different landscape geologically. And so while there were heavy metals present in the sediments, none of them were added there. They were all heavy metals that were naturally available in the landscape. So arsenic, for example, is one of the metals that was out there. Lots of iron, lots of aluminum. That's why they call it Iron Gate. It was called Iron Gate before the dam was put there, just because the rocks were so iron rich. And so those were the heavy metals present in the sediments, were all ones that were naturally occurring. There was no more heavy metal present in the sediments in the reservoirs than there were in the rocks surrounding the reservoirs. And so when we drained those reservoirs, you naturally expected to, as all that material is moving through the system, you see an increase in heavy metals, but then since then it's gone back down.
Okay, great. Thanks, Fran. Next question. How much remaining sediment from behind the dams do you expect to continue to wash downstream, and how long will it be to reach a steady state condition for sediment loads?
So there is sediment transport happening now. A big part of right now, so we're having huge flows in the river this year, right? So like I said, last year, we very specifically held drawdown to the rate of 3,600 CFS. We actually never even got even close to that, because again, the water coming into the system was so low last year. And so we generally hovered around 2,500. This winter, we have so much water in the system. At one point this was about 2-3 weeks ago, there was 11,000 CFS at Iron Gate. So the river is definitely reaching new heights, scrubbing away material, but those high flows, right, moving that sediment now is going to prevent it later on down the line. In terms of like baseline river clarity, all the geologists and hydrologists expected that we'll return to what's called baseline clarity on the Klamath River, probably about 24 months after the initial drawdown period. So we're about a year out from that, right? We're 1 year in, we probably have another year of seeing clarity impacts, but the majority of the sediment has already moved through the system.
All right, thanks. Let's see. Next question, fascinating presentation, thank you. Will the recording be shared to rewatch later? I can answer that. The recordings for all the water seminar series presentations are on our website, and it's just under the water seminar series button. Alejandra, since this is your question, I will respond to your email with the direct link, and it'll be up within I would say definitely up by Monday. So it'll be available by Monday. All right. What is the typical lifespan of a hydroelectric dam?
That's a great question. I can't speak to the typical lifespan at large. I can say that definitely from these dams, right? Well, let's start off first that different ones have different lifespans from safety perspective, right? Something before, I grew up downstream of the dams on the Klamath River, and something I didn't realize until I was working on the removal of these dams was just how dangerous Iron Gate was, right? So like I noted, it was a big earthen dam. So some dams have shorter lifespans because they didn't quite have the forethought to build them the right way. So Iron Gate, as an example, is actually raised twice in its lifetime. It's a really big piece of misinformation that's prevalent here in Siskiyou County that Iron Gate Dam was built after the 64 flood, which was a huge flood year here on the river, as flood control prevention, right? Actually, Iron Gate was built, it was completed in 62 before the flood and was badly damaged during the flood and nearly overtopped. So it was forced to be raised, right? And then after hydraulic analysis, around the 97 flood, it was actually raised again. So it was raised twice in his lifetime just from a safety perspective. And so with these dams, it's difficult to speak to what their lifespan is completely, right? Because it depends on what their purpose is and how they're constructed and safety and environmental considerations, right? Ultimately, these dams were removed because to bring them up to modern safety and environmental standards would have cost nearly twice the cost to actually remove these dams, right? A huge part of the contributing factor to that cost is I showed you how Copco number 2 dewatered that river canyon there. So the fish ladder to overtop Copco number 1 would have had to been 2 miles long. And so I'm not sure what the average lifespan is for dams in America. I'm sure American Rivers probably has that fact somewhere up on their website, but there's also just a lot of different considerations. And a big part of it, though, is safety.
All right, great. Thanks, Ren. Next question. Great presentation, $500 million budget as cost. Are there projections to added revenue to the state through salmon fishing improvements over the next decade or so? Or do we have to wait to see what the salmon do?
I think we definitely have to wait and see what the salmon do. I mean, there is definitely economic incentives, right? I haven't checked the cost of a barrel of oil recently, but last year, it was true that the cost of a single salmon, a salmon costs more than a barrel of oil, right? So salmon have a huge economic value. Not just in terms of the commercial or independent or guiding salmon industries, right, and those contributions. I'll say that on the Klamath River itself, faces to gain some serious economic improvements because these dams were heavily impairing water quality. Like, this is me speaking from personal experience, but I watched communities on the Klamath River really deteriorate as kind of the landscapes and the river has deteriorated around us, right? People don't want to come to town and go boating in a river that is so unhealthy. So we've really seen, and similarly, people don't want to come to town and go salmon fishing or steelhead fishing when you just can't catch anything anymore. So I think that there's a lot of economic opportunities from a salmon, perspective for commercial fishermen, but then also for the people who live along the river. Also note that a part of our project too was bringing, some economic opportunities to the area. So for the total budget and for the respective contractors, the goals was that 5% of the total project budget would go to local contractors and another 5% of the total project budget would go to tribal contractors. So that was a lot of locals that were employed during the dam removal process as well.
All right, thank you. Next question. Let's see. What is the main difference between hydroelectric and others, i.e. Shasta dams? I think the question is, what's the difference between hydroelectric impact or output from the dams you're dealing with and a large dam like Shasta Dam?
Like electricity impact, you mean? Or
I
like
think so.
differences in environment? So, like I said, at a certain point, these facilities were really old. So I think that the whole project, and this is available on our website, so you can go fact check me. Because I'm pretty sure it was the project as a whole had the capacity to generate 163 megawatts, which is not a ton of energy. And that was previously the total capacity, because in reality, they generated around 80 megawatts before we turned them all off. So that's not a lot of electricity in the grand scheme of things. And one of the contributing factors, right? Not as much water in the Klamath River as there was previously. And the second one, in some of these facilities are over 100 years old, right? So a good example of just how out of date a lot of this technology was is that when we initiated drawdown, So we would actually utilize the powerhouses all during the deconstruction of Copco number two, right? Because we had to control the flows in the river, and you utilize the powerhouses to do that. So it wasn't until we initiated drawdown at the three reservoirs that we actually turned off the powerhouses. And then Pacificor had the opportunity to come and take anything they wanted from the powerhouses, right? And the only thing they really took were the fire extinguishers and the computers that allowed them to remotely operate the facilities from Idaho, because all of the other stuff in it was just so defunct, right? It couldn't even be reused or repurposed elsewhere. And then one thing I'll notice about Shasta Dam, which also does it, Shasta Dam does provide flood control. It does provide irrigation water, and I believe also it generates electricity, but the flows also come out of it differently. So pretty different situations with those various dams.
All right, great. Let's see, the next question, there's actually three questions. I'll just do one at a time. Such an inspiring project. Thank you for this excellent presentation. The questions are, what are the visual signs of low DO?
So it was so trippy. You know, the first time I saw it happen last, I believe the first crash, it was in February. So I think it was February 27th, maybe? No, it must have been sooner than that. I'm trying to think. February 3rd, that was it. February 3rd of last year, that as all this dead organic material is getting stirred up, right? And you see the oxygen start to crash, it's such deoxygenated material, it really truly sucks up all the oxygen in the water. So you can see the signs. First of all, there's smells, because there's a chemical process happening as well. So there's a distinctive smell that you can smell as it starts to crash. And then the other thing was that there was just no bubbles in the water, right? So like as the DO goes away, once it hits zero, there's not a single bubble in the water. So living on the Klamath River, and I was about 20 miles downstream of the dams, I watched the river have bubbles. Like as the water was going over these like, you know, whitewater spots, right? The water went from white to black. It was incredibly trippy. It looked like oil going over the rocks. I want to be clear, there was no oil in it, but it was very similar in its look. And it's just that there was so much deoxygenated material in there. It wasn't a mudslide. It wasn't from the sheer volume of material, but it was sucking all the oxygen out of it. So the water just, there was no bubbles in these rapids. The water just slid over the rocks. It was very trippy. And again, I want to emphasize that's not from the sheer volume of material, but just from the reactions happening that it's sucking all the oxygen out of the water itself. So it's the lack of bubbles. So like at the Coffer Dam breach, right? I could see as it was happening, as the water going kind of over the Coffer Dam area that started off kind of as white water, changed color, and then lost its bubbles.
Okay, great. And let's see, same person, two more questions. Well, actually, I can combine these into one question. I like this question. What is the best time to go see the restoration area, especially the poppies blooming? And what opportunities are there for members of the public to visit the project areas?
So the best time of year is like May, June, because that's when all the wildflowers that they've been planting are going to be blooming. It was really striking and beautiful last year. And this year, I expect it'll be even more impressive, right? Since the second go around. And so definitely like kind of late May, I would recommend, early June. In terms of for opportunities for members of the public, dam removal's done, the restoration's ongoing, but now a lot of the KRRC folks are turning their attention towards the building out of recreation areas. So in total, we're building 5 new recreation areas that have boat ramps and things like that so that people can go explore these new stretches. Well, they're not new stretches of river, but like stretches of river that people have not had the opportunity to go boating on for over 100 years. So 5 new recreation sites. And then there's also going to be a whole trail system as well. This is a good thing. I should have noted this in my presentation, but that the people who lived in that area prior to the dams were the descendants of the Shasta Indian Nation. So while the Karuk and the Yurok tribe had a huge role in advocating for dam removal, the Shasta are the dams that were actually kind of upstream of those tribes and the group that the dams were built on top of. They lost the last of their land base with the construction of the Copco Dam. And presently, KRRC owns all the former dam sites. So when PacifiCorp surrendered the project, they gave KRRC the dams and then all the associated lands. So that includes the reservoirs, areas where there was pipelines, powerhouses, etc. And it's about 8,000 acres in total, 1,000 acres in Oregon, 7,000 acres in California. And when we're done with the restoration and monitoring, per the KHSA, we will surrender those lands to California and Oregon or their third-party designee. And the state of California has indicated that one of their designees is the Shasta Indian Nation. So there's about over 2,000 acres that will be returned to the Shasta Indian Nation following the completion of the restoration as well. And there's it's called the Heritage Trail System, where there's going to be a lot of educational resources where you can go hike for a couple miles between two of the recreation sites, learn some facts about dam removal, learn about the people who were originally there. And the last one more fun fact I want to share about that area is that kind of canyon area and either side on it are known as Kikacheki. So that'll be the correct term to search for when you're looking for the completion of those rec sites, is kind of the Kikacheki recreation area.
All right, thanks, friend. Just a couple more questions. Did any water rights change due to these dam removals?
PacifiCorp did, right? And that's about it, I believe, because PacifiCorp had different water rights associated with the operations of these dams. So they don't have those water rights anymore. But again, these dams didn't provide any irrigation water or anything like that, drinking water, none of that. So none of that has changed.
Next question, regarding the powerhouses, were they preserved as a historical monument or for any other purpose?
So by the request of the Shasta Indian Nation, we actually did save the Copco #2 powerhouse. It's located in a very important area to them, and they're going to retrofit it and use it. It's likely to become an interpretive center, actually. But that'll take a couple years to fix that place up.
All right, the next email isn't really a question. It says, no question, just a thank you. Great story about the Klamath.
All right.
And let's see, we have time for these last two. It sounds like you kept the flows at safe levels, but did you need to warn downstream campers or residents right before the increased flows?
So before our flows, I sent out a letter to everybody who lives on the river just to warn them that these flows, that there would be an increase in flows, but also to prepare them for what they were going to see sedimentation wise, right? It was a very visual part of the process for everybody that lived on the river. But the flows, so I did notify people, but I should note that the flows were not outside any of the regular flows on the Klamath River. And just to emphasize this point a little bit is that, again, Iron Gate was not operated for flood control. So it was pretty much kept at its tippy top full capacity because the water was pulled from just under the surface to operate that powerhouse. And so when we did have a lot of rain or something like that, the water would just go over the spillway. So the flows were within the normal range, but we did notify people.
Right, that makes sense. See, us folks in Sacramento, we know that when there's huge flood control releases, they send helicopters down the American River path, warning people that there's going to be huge changes. Mm-hmm. Let's see. Final question. Are there other areas in California where the removal of dams is being considered?
Yes, and I want to be clear that KRRC is not working on any of these dam removals. KRRC existed for the sole purpose of removing these dams, and that's all that we work on. But there are other dam removals occurring in California. I know that they're being considered on the Eel River, for instance.
Okay, great. Thank you, Rin. Thanks so much for answering all the questions in such detail. And on behalf of OWP and all of today's participants, we want to thank you for an excellent presentation on undamming the Klamath, a topic that certainly has everybody's attention these days. And again, I also want to thank all our listeners, and I hope everyone has a nice weekend. Take care.
All right. Thank you for having me.